Okay, so let us next see the familiar formulas of differentiation. We already know these things from calculus, but again of course we are going to see this here and we will prove it also, not now in this video but in the community section. And that is why this theorem has been named differential calculus, and it's also known as the algebra of derivatives. So our setup is usual. We have a subset x of the set of real numbers, and there is a point x0 or x0 in x which is also a limit point of x. We need this condition in order to define a function having derivative at that point x0. We already know these things. Okay. And then we also have two functions f and g, both real valued and both of them having x as their common domain. Alright, then there are some parts. Okay. And the first part is of course about the constant function. If f is a constant function on x, i.e., if there exists a real number c such that f of x is constantly c for all x in the domain x, then f is differentiable at x0. At x0 on x, that however is understood, so we do not write every time on x. We just merely mention the point at which we are considering differentiability. Then f is differentiable at x0 and the derivative of f at x0 is of course 0. And this is just that thing which we already know, that when you differentiate a constant function, no matter at any point actually, then the derivative is, then you get 0. That's just it. Differentiating a constant gives you 0. It's just that same thing. Then part B. In part B we have the identity function. Well, we cannot actually call it the identity function, but okay, let's see. Let's see what this part says. If f of x is equal to x for all x belonging to x, then also f is differentiable at x0, and this time the derivative at x0 has value 1. Why was I saying just now that we cannot really call this the identity function, although the rule for f looks like that? It's because by definition an identity function on a set A must have domain A as well as range A. And then of course the rule for f should be this. We however have domain x and range R, and x may not be R itself. Okay, it's just a subset of R. It can be any subset. So that's why we just write like this. We do not call it the identity function on x. If we had x here as well, we would have had identity function. But anyway, that's not what matters. What matters is that when you differentiate this formula with respect to x, you get 1. It does not matter at what point you are doing it. And then of course we have our familiar sum rule. If f and g are both differentiable at x naught, then f plus g is also differentiable at x naught. And the derivative of f plus g at x naught is the sum of the derivatives of f and g at x naught, and they of course exist. That is our hypothesis, because f and g are differentiable at x naught. So that is the sum rule. And then part D is the product rule. We all know these things. The product rule is also well known, although the formula is not as straightforward as the sum rule. Okay, it's not that the product, the derivative of the product of two functions is the product of their derivatives. It's not that. It's something else. If, again, f and g are both differentiable at x naught, then fg, their product, is also differentiable at x naught, and the derivative of fg at x naught is the derivative of f at x naught times the value of g at x naught plus the value of f at x naught times the derivative of g at x naught. Okay. Next, I think we have the constant multiple rule. Yes. This, however, hasn't been given any name. If C is any real number and F is differentiable at x naught, then the function CF obtained by multiplying f by c, and we already know what it means. Okay, its value at any point x in the domain of f is c times the value of f at x. Is also differentiable at x naught, and this is rather easy. This is another of the familiar things which we always use while differentiating functions in calculus. It is that c times f prime of x naught. And the way we remember this is simply whenever you encounter a constant, Okay. For example, you see this type of notation is not what we usually use. We instead would write this like this. Like this. And the right hand side of the above equation, if you write in this notation, it will look like this. Well, of course, you can of course also say that you are doing all these things at x equal to x naught. So, the way we remember this is that because C is constant, C comes out of the differentiation process. It's just that same thing. Okay. And then the next one is difference rule. If f and g are both differentiable at x naught, then so is f difference g or f minus g. Then so is f minus g, and the derivative of f minus g at x naught is the derivative of f at x naught minus the derivative of g at x naught. And there are two more rules, two more parts. But I think I already need some ink. Just give me a moment, okay? The two remaining are about, one of them is the derivative of the reciprocal of a function, and the other one is the derivative of the quotient of two functions. Your familiar quotient rule for differentiation. Okay, so the next one is the reciprocal. So this is part F and this is G. If G does not vanish on X, i.e., if G of X is not equal to 0 for all X in X, and if G is differentiable at x naught, then the reciprocal of G is also differentiable at x naught, and the formula for the derivative is this. And the derivative of 1 over g at x naught is minus the derivative of g at x naught divided by the square of the value of g at x naught. Okay, that is the formula. And the last one is the quotient rule. This is also nothing unfamiliar to us. We also know what the quotient rule, or in fact what the formula is. Although this is the most complicated among all these. If f and g are both differentiable at x naught and g does not vanish on x, which of course just means this, that no matter what point x you choose from x, you evaluate g at that point, you get a non-zero real number. Then the function f over g is also differentiable at x, and I will write the formula on that side. A storm is raging outside and there's heavy rain. The rain is a big relief from the extreme heat, but at the same time the power is gone. So the formula for the derivative of f over g at x naught is this. In the denominator you have the square of this, like what you have there, and then in the numerator you have g of x naught times the derivative of f at x naught minus f of x naught times the derivative of g at x naught. Recall that we remembered this formula like this. The denominator function of course appears in the denominator and we need to square its value at x naught. And then when you look at the numerator, you do not do anything to g first. You differentiate f, but then you keep f intact and differentiate g. And unlike the product formula where you have a plus sign in the middle, here you have a minus sign. So in the product formula, it does not really matter which function you are differentiating first, because a sum is commutative always. Here, however, you should remember that the term which does not have a minus sign before it, that should have the function value, the denominator value, multiplied by the derivative of the numerator, and then minus the other thing. Okay. And the product rule, of course, is by Leibniz. It's known as Leibniz rule. Named after, of course, Gottfried Wilhelm Leibniz. And that is actually a remark, okay? That's a remark which appears just after this statement of this theorem. Okay, so it's named after Leibniz. And the proof, of course, we won't do here. For the proof, one has to see exercise 4. Now after this, the author discusses one example. Discusses means he just simply mentions it, but let's see what it is. You consider this function. Let us just see how we can use the various parts of this above theorem to find the derivative of an actual function. And the rule for this function is this. x minus 2 divided by x minus 1. And you can see that because of this denominator, we had to remove 1 from r, because at 1 this is meaningless. Okay. Now we are going to carefully see all the things that we have in the theorem in this special case. First of all, let's just choose one point. You see that here our x is this. If you do not like this way of writing a subset of R, you also have the option of writing this instead. Okay, it's the real line from which the single point has been removed, which has created two intervals. Okay. Now, if you take any point x naught in this x, will it be a limit point of x? Yes, because we have already proved, before while studying limit points, that inside any such interval, and we have open intervals also, every point is a limit point. Okay, so there is in fact no problem in considering x naught in x. You can consider any point of x that will be a limit point of x. Fine. Now say we want to conclude that our f is differentiable at that x naught. How can we do so? We can do so by applying the several parts of the above theorem. Let's see how. You see, this function f in fact is a quotient of two functions. Alright. Let me just name those two functions, because we are already calling this entire function f, so we cannot call this f and this g. Instead, let me just call this function alpha, where alpha of x is x minus 2. You may object that what is the reason for removing 1 from the domain of this function, since you can actually put 1 here, but that's not the point. You see, we have to consider two functions whose domains are common. Okay, there is only one domain, because the domain of x minus 1 has to be this only. This only means this is the largest possible, and that's the one we are considering here. So here also you cannot actually consider alpha on the entirety of R. Fine, that's okay. But we also have this function beta. And beta of x is of course x minus 1. Alright. Now, are alpha and beta both differentiable at x naught? The answer is yes. Why? How? You see, that's because alpha and beta themselves are also differences of functions. Say you call the function I from r minus 1 to r, which is the identity function. Again, I am calling this the identity function, and it's not strictly the identity function, but its rule is that of the identity function. Okay. Now, what was that part where we concluded that this is differentiable? Part B. By part B, we know that I is differentiable, and I prime of x naught is equal to 1. And you can also consider two other functions, say gamma Let me just write them together. Okay, gamma and delta both from r minus 1 to r. What is gamma? Gamma is a constant function and gamma of x is equal to 2. Delta is also a constant function and delta of x is equal to 1. Okay, so both thunder and lightning. So both gamma and delta are also differentiable, and this is by part A. By part A, gamma and delta are both differentiable at x naught, and the derivatives are both 0. Alright. Now, so what does that ultimately imply? There is one more thing, however. You see, differentiability of I, differentiability of gamma and differentiability of delta tells us what? It tells us that alpha is differentiable at x naught and alpha prime of x naught is simply equal to I prime at x naught minus, I think this one is delta, yeah. No, that is beta, so this is gamma. Gamma prime at x naught. So this will be what? 1 minus 0 equal to 1, right? And what about beta prime at x naught? Beta prime at x naught is equal to I prime of x naught minus delta prime at x naught. So this is again 1 minus 0 equal to 1. Alright. Okay. So what is that other requirement that we have before applying the quotient rule? It is that the denominator function should never vanish on its domain. Does this function ever vanish? Well, it vanishes. This formula can give you 0 only when x is equal to 1. However, that 1 is not available in our x, capital X. And that is why for all x, in fact the x naught we have chosen, it's actually any point here in this set. For that x naught, beta x naught is not equal to 0. So we have all the pieces with us so that we can apply the quotient rule to our original function f. So by the quotient rule, first of all, the first conclusion is that f is differentiable at x naught, and the next thing is its derivative. And that derivative by the formula for the derivative is this: beta of x naught times alpha prime x naught minus alpha of x naught times, let me write here, beta prime x naught. Okay. Now what is beta of x naught? X naught minus 1 square. What is this here? Again x naught minus 1 times, what is alpha prime of x naught? 1 minus, what is alpha of x naught? X naught minus 2 times, what is beta prime x naught? 1. And if you simplify the numerator, you will see that you are getting 1, and in the denominator you have this. So this is the derivative of our function f at x naught. The author did not go through these steps, of course, because these are just something basic which we already have done in calculus many times, but I thought of showing it in details once more. All right. Now next, we have the very important chain rule. When you have two functions, both differentiable at suitable points, then their composition is also differentiable. Let's see what that chain rule is. This is also something we know and we have used it innumerable times. 10, 1, 15. Chain rule. It starts off like this. Let x and y be non-empty subsets of R. Let x naught in X be a limit point of X, and let y naught be a point in Y, and let this be also a limit point of Y. Okay. Now we have two functions. Let f be a function from x into y, be a function that is differentiable at x naught and such that, or we can simply write and f of x naught is equal to y naught. Okay, so this is one function and the restrictions imposed on that function. There is another one. Let g from y into R be a function that is differentiable at that point y naught. Then the conclusion is this: the composition G composition f, which of course is a function from x into R, is differentiable at x naught, and the derivative of this composition at x naught is the product of the derivative of y at y naught and the derivative of f at x naught. In this form, the chain rule, which is already familiar to us, looks very strange. It does not immediately feel like the chain rule we have seen in calculus texts, but we will come to that, okay? In this next remark itself, we are going to go back to our familiar calculus notation and see how the chain rule looks. And the proof of this, of course, is again one of the exercises which we will do afterwards. The proofs of none of these results is actually very tough. We just need to carefully arrange the things, see what the hypotheses are, and just put the bits and parts in their proper places. When all the things fall in place, you will have the proof. That's it. That's just it. Now let us see this. Well, yeah, okay, but before that though, there is an example. And by the way, the proof of this is actually exercise 7. Yeah. So before discussing that notation thing, let us see this example, which will of course illustrate the chain rule. And here we have two functions, one of which is our f from the previous discussion, whose derivative we calculated. Consider the function f which of course is given by this rule, and another function g and the rule for g is simple, g is just the square function. Okay. Now, are we able to apply the chain rule? Let us first see what the hypotheses are. What shall we do? We want to first of all choose a point x0 in the wire. In the domain of f, let us identify the sets over there here in this situation. For us now, x is r difference 1, y is r, and r of course is r. Okay, so f is a function from x into y, and g is a function from y into r. Fine. And we are now arbitrarily choosing any point x in x. We have already seen before in that example, because after all we are considering only that function f along with this new g. We have already seen that any point x0 in x is a limit point of capital X. So it can be chosen. Is f differentiable at x0? Yes. And we know its derivative also. We know this. Okay, this is something we already know. Now, what is f of x0? F of x0 is this, which is in capital Y. Is it? Yes, it is, because this is a real number. It is in Y. Now, is the function g differentiable at this point? Yes, g is differentiable. In fact, g is differentiable at every real number, and its derivative is 2y. I mean, here we are calling the independent variable y, that's why. Okay, so g is also differentiable. In particular, it's differentiable at every point. In particular, it's differentiable at f of x0, which we denote by y0. Okay, and we know that this is 2 times f of x0, because that's the derivative of the square function. So this is 2 times x0 minus 2 divided by x0 minus 1. So yes, we do have everything. Oh, and by the way, is this point a limit point of y? That should also be there. No? Yes, because y is the entirety of R. Every real number is a limit point of the set of real numbers. So yes, we can apply the chain rule, and when we do so, we first get the conclusion that the composition of f and g is differentiable at x0, and then we get this formula. Using this formula, we get the derivative of the composition at x naught to be g prime of y naught, which is this. Times f prime of x naught, which is this. So that is the derivative of the composition. And the composite function, if you just want to see the formula, it looks like this. Now, instead of going through all the hypotheses, all the technicalities, if you simply apply the routine procedure for differentiating this function from your calculus course, what will you do? First, you differentiate this entire thing, treating x minus 2 divided by x minus 1 as a single variable. So you get 2 times that thing, which is what we are getting. And then you differentiate this quotient using the quotient rule, which we did before, and we got this. So that's how you get the chain rule. And now comes the remark about why this formula as written here doesn't look like the one we are familiar with from calculus. What? I think I messed up the number. Okay, this is 17. I wrote 7. It does not really matter, but still. No, still wrong. This is 16. This remark is item number 17. You rectify the numbers, okay? It's not a big deal. If one writes y for f of x and z for g of y, then you go back to the equation that is there in chain rule and you get this very nice looking formula, which is in fact the one we have seen in calculus texts, but the author says that it's somewhat misleading, and it actually is misleading, although it looks very beautiful and appealing, and at the same time it's easy to remember. But the way we remember it, in fact, is also the cause for all the trouble. We remember it like this: cancel dy dy, you have dz divided by dx, but actually it's not division. It's not division. In fact, we have not really defined these quantities separately. Okay, they can be defined, but we haven't done so in this text. They can be defined means, loosely speaking, they are treated as infinitesimal quantities, infinitely small positive quantities which are smaller than any positive real number. So these are actually not real numbers. These are known as differentials, and they can be made rigorous using some tools which the author has mentioned, like tangent vectors, derivative maps, something he mentions. I also don't know what those things are, but he says that those are beyond the scope of this text, so we won't do it here. And the situation becomes even more complicated and confusing once one goes to functions of several variables. So he does mention something like this. Say f is a function of two variables, say x1 and x2, and they themselves are functions of a single variable t, then by the multivariable chain rule, the multiple variable version of this result, the derivative of f with respect to t is the partial derivative of f with respect to x1 times the derivative of x1 with respect to t plus del f del x2 times dx2 dt. So, if one really is treating these differentials as real numbers, they are not, but if one say unknowingly, accidentally treats them as real numbers, then these things seem to get cancelled and it does not really match. Okay, so because of these confusions, the author has decided, and it's a wise choice, to not use these notations, well-known notations. And that's how the section ends. After this, we of course have many exercises which we will solve in the community section. And that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.